Hello everyone, I'm sure you are doing awesome. So in this video, we are going to explain to you some advanced orchestrator designs for AI system and why we need it. So let's take one example. Imagine you are building a billing microservice. Given this line items and the discount rule, what would be the final payable amount? Now, historically, you have known that mathematics with the maths, your particular LLM is little weak. But if you do it repeatedly, mostly it gives you correct answer. Like maybe 8 out of 10 times, it gives you correct answer. And in the two times, it's it is outrightly wrong. So in this case, what exactly we can do? A very popular concept of backend or the distributed system is being used here. So if you know, in the distributed databases, we achieve strong consistency through quorum reads. So what exactly quorum reads are? Suppose there are three replica through which I am operating. The database is getting operated through three replicas. So what we try to do is we will get all the three replicas, or we will try to get all the three replicas output. And even if we get the not the 100% output from all the replica, if we get the majority output, that majority output we take it as an answer. So the same pattern we apply in our LLMs as well. So just to recap, while getting the data from the databases, suppose we are getting the uh, we are syncing the data into the three replicas, and once we get all the confirmation, then we at first decide to move. But even if like one replica is not getting synced in a real time, we are okay, right? The majority of the replicas, or there is a certain quorum number that we decide that if this many number of replicas have the correct data, then I take it as a quorum or a consensus. So we call it as a like self consistency or ensemble method as well. So by taking that consensus, we generally proceed. So this self consistency imposing, what we generally do is we do in our LLM by running the prompt 5 times and by getting the final answer as the majority vote. So uh, technically it looks like this. So as you can see over here, we will have the same prompt again and again. This will be like in a for loop or in a while loop with a max. We will do with a reasoning max number. We will keep on running this thing in the LLM throughout the LLM as our responses. Whatever the majority answer that we will get, that is that will be our answer. So we also vary temperature over here. So if you have covered it since the first video, you know that the temperature 0, that means it's a deterministic one. And the more I move towards the number 1, it means it is a diversified sample. So the creativity increases. So if you are writing a poem sort of a thing, then probably the temperature mode, if it is towards 1, it is better. And if you are doing this kind of mathematical calculation, then temperature towards 0, it gives you further deterministic approach. So 0 is like deterministic, and the temperature 1 is further sampling sampling distribution that we have. Now if you run the same prompt 5 times with this temperature greater than equal to 0, each run takes a slightly different reasoning path, and some run makes the mistake, but they will make different mistakes, and the correct answer appears more consistently across the run. So now we know that it is a mathematical problem, right? So maybe we will just vary it a little bit, like one run with zero point 0.1, the next run with 0.15. Of course, with 0 we will do one run, like zero point 0 we are going to do one run. So in this way, uh, the more towards more relying on the deterministic side, we are going to take each of this run, and it is like asking five different experts the same question, and although they might give different answer, but there will be some point of consensus, and that point of consensus we are going to take. So the mathematical problem that we were thinking, given that there are some line items and there are some discounted rate, what will be the final payable amount? Suppose there are three different numbers, like at one places we get $100, in the second places we get somewhere around $115, and the same thing we get 115 one more time. So in that case we know that the going by the probability, so this 115 has the highest probability of getting the answer. So your answer will be calculated on this front. So this is how the quorum concept of this works. To explain this through example, we are going to take a classic example. Suppose we want to classify the sentiment, like this is a sentiment analysis bot sort of a thing that we have. Now, for this sentiment analysis, suppose we are getting a this sort of mm, response from the user about a product, that this product is not bad for this price. Now, how do I understand this not bad? If I go by simple negative connotations of it, so it will focus on the bad, and it will say that it is giving a negative reply, and s- whether it is actually providing good value or not, that will be the positive one, right? So here what exactly the user is trying to say is it is a okay kind of a value for the product. So probably it is somewhere around the neutral, but that you or me, while discussing as a human, we understand. How does the LLM is going to understand this? Let's see it through code. So this particular code is a self-consistency sentiment analysis that we are running with a n equal to 5, that it will run for n times. Okay, so we are creating a async counter for n times it is going to run as a task. So here you see this LLM call async is happening with this temperature, and what this async IO gather will do is it is going to gather the output of this tasks. So we are going to put all our vote counts here, and we are going to return that what exactly is the majority sentiment, and what exactly is the confidence we are getting, and what are the different votes that we were getting. So the vote counts we are already putting it into here as a counter, and the output will be very interesting. It is going to tell us that what is the majority sentiment that we are getting through this iteration, and what exactly is the confidence of it, and also it will give us the actual vote counts. So for example, out of these five counters, we got the positive as 3 and the neutral as 2. So it is more towards positive. That is why the sentiment is being deducted as a positive. So the interpretation is simple: 3 out of 5 runs classified as positive. The confidence is 60%. It is not unanimous, but it is a clear majority, right? And the 0 negative votes are there. So it is a strong signal that the review isn't negative. So this is how the LLM further going to analyze this. But all responses are ideally not equal. So instead of this direct voting, generally there is one more technique that is being come into the mainstream as a very popular system, that is called weighted voting. So in this process, suppose we are getting 5 responses, okay, and in the 5 responses, the first one has the positive, and the positive one has a very high confidence rate, and the second one is also having a very high confidence rate as a positive. And when we see the neutrals having the confidence on a little lesser side. So in a simple majority, if we just keep on calculating it, that how many votes positive is getting and what exactly is the confidence score it is getting out of it, so the weighted vote will come as 2.55 for positive, Whereas for neutral, it will come as 1.15. So again, this is a way more pragmatic and practical approach than just calculating that what exactly is the sentiment. So alongside these votes, we also have to keep on adding the uh, confidences as well. So if we add the confidence, we will get the actual weighted score, and that is a way better uh, parameters to find out that what exactly is the output that we are looking at. Now please go through this question. I am sure that you will be able to answer this without a hitch. Just this is a very practical problem. I will just explain it to you. In terms of a medical system, whenever we are getting some accuracy, even if the accuracy is somewhere around 92%, it is not a very good accuracy, right? Because it might be like that particular diagnosis, if not given to the patient in a proper time, it might be fatal for his health. Or if it is a little bit here and there, little wrong, then in the medical context, 92% can be said that it is not at all sufficient. 8% error rate means 8 out of 100 patients are misdiagnosed. And if it is like a fatal disease which can cause mortality, then this is a non-negotiable thing that this sort of models cannot go. So suppose with this context in mind, you are building an AI assistant. It analyzes the patient's symptoms, and they should whether they should go to the emergency, or they should schedule a doctor appointment, or they can just stay at home and take some home care. All these things are dependent upon your AI assistant's whatever the opinion it gives. Now the constraint is the false negative is completely unacceptable. Like in case you are missing a serious condition and you are asking that patient to stay at home, then it is going to be completely problematic, and can be very fatal for the patient itself. And if it is a false positive, you are sending everyone to the emergency visit, then it is again a very costly. Okay, so you cannot afford this sort of a hallucination, or this sort of like false negative or false positive here. And if you are applying chain of thought with a single inference, if you are achieving 92%, it is not at all achievable. But here the thing is that in case we apply our weighted voting pattern, then we can go very close to 100. There is a 99.9% accuracy we can achieve. And how do we exactly design this kind of system? So generally we put multiple layers around it. So in the layer one, we will have all the red flags, like if there is a certain chest pain is there, or if there is a pain plus breathlessness, those kind of conditions are there, then there is no option, but we have to call the 911 or the local emergency number and take the patient to the emergency. If there is no red flag, then only the layer 2 will come, which in which there will be the COT, or the chain of thought will come in play. So in this symptom detection bot, just note that COT comes in the layer 2. Okay, so in the layer 2, what would happen is, if we are defining n equal to 7, and if we keep on varying the temperature a little bit, so out with that, if we get like a 7 out of 7 agreeing, then that means it's 100% confidence. If we get a 6 out of 7, that means 90%. And if it is kind of a split vote, so these conditions are generally, we call it as a split vote. That means a manual review will be required. So you see, although on top of it, like we are building a system like a symptom detection bot, but our chain of thoughts and the decision based on the chain of thought, whatever the decision matrices we have, that may vary in multitude of way. And only in the layer 2, the interesting part, the only in the layer 2, the COT, or the chain of thought, is being triggered. So if you just see the transition that we are taking gradually, without much complicacy only, we are gradually going into the agent loop, which is the core of the today's AI systems, the AI agents. The system can break down complex problem and execute the subtask and self-correct over the time. So all the chain of thought that we discussed, or all the concept of the weighted voting, the quorum, everything that we have discussed till now, everything will come together, and it will help us to create the AI agent that we were talking about. So now let's take a little bit of paradigm shift and try to understand what exactly is a AI agent is. So by definition, if I have to say, in a traditional LLM, what we were doing is we were doing this one shot, and over the time we have seen we have moved towards the multi-shot, and from the multi-shot we have come into a weighted voting, and that based on that weighted voting we are able to take different decisions. So here you see this there is a certain termination condition, like suppose in our programming paradigm, like if we have to compare it with a recursion or a upper limit of a for loop. So with those sort of a decision matrix, when we keep on building within our AI agent, we have a certain exit point, and there are few important core components in a agent where it keep on where it keep on taking decision, and what are the different components comes together to aid that decision. Let's take a look into that. So these are the very important concepts. So the first thing is the state. State is basically the history of the accumulated context. Like in your chat GPT conversation or with any bot, if you are conversing, whatever the first thing that you have said to it will keep on taking it in a queue, and with that it builds its own state. And then there is a orchestrator. Orchestrator is basically the while loop that decide whether I should be continuing from this step to the next or I should stop. And then there is executor. Executor is a stateless function that processes the current state. So it takes the current state and it takes all the input, and then it passes on to executor or the LLM, and from the LLM it get the response, and it might do some sort of a classification, some sort of a quorum, the weighted averages, everything on top of it. So that is the part of the uh, that that is what the executor does. Like by talking to LLM, it try to get the concise response. And then there is a termination or a exit condition is also there, which determines a logic that okay, now I am completed, I do not have to go any further from now. So let's take a example of a simple calculator. So, if I take you to a little bit back in a time machine, maybe 3 years back or 4 years back, where even GPT 3.5 was not there, if I am passing something into the LLM just to do this simple kind of a calculation, it might hallucinate a lot, because as we were talking that LLM is mostly able to generate the next token. It is not designed in any way unless we do explicitly something around it to do this kind of calculation. So we are going to take the agent loop approach here, and how the agent loop is look like. So let's not go into the code. Let's try to understand what is happening over here with the controller, executor, and the state. So user is going to make a request to the controller or the orchestrator that I want to solve this problem. This problem can be something as simple as this. Okay. And after user passes this problem, controller is going to initialize a history with a system prompt and a problem. It will say that you are a great mathematical problem solver. That will be our system prompt, and this is the problem that we are going to pass on to our state. Now within the state, I will have the problem and the prompt, and using this information I will keep on iterating over again and again through my executor to understand that whether I am getting a valid response or not. So it can be a valid JSON, it can be a error JSON, and whatever the final answer that I am getting, it is completely based on that weighted approach that we took earlier, right? Over here, the weighted voting that we took, it is quite similar to that, but I'm not calling out the weighted voting explicitly here. But based on this, uh, the final answer will be done on this iteration. This thing is called as a agent loop, and which is the very basic foundation or the paradigm uh, upon which the whole agent loop architecture and everything is there. So in case you have understood the weighted calculations of voting pattern, the quorum pattern, and understanding the different confidences with different temperatures, how we can get different outputs. So then probably you are very close to understand what exactly a AI agent is, or rather how internally a AI agent works. In this step, one process probably you understood that if you are taking the state management here, so every single call that is happening, that is going to get stored in the state. So in the memory, after each iteration, the history array will keep on getting built up. So a memory management challenge arises here, that in each iteration, if the history array grows by some X tokens, then you see that we have a basic system prompt, we have a user problem, step one response, step two response. With all these things, it will go to probably 10,000 tokens for a single questions. Okay, a very simple question with a iteration of 10 or a iteration of 50 for very complex problems maybe. And what would happen is eventually with this, eventually you will exceed the context window. Eventually, you are going to completely exceed the context window, and any example problem like this is going to require a multi-step reasoning, like the parsing the prices, the computing the Monday's revenue, the applying that 15% increase. Just take a pause and you will see that this is not a very straightforward problem to solve, or not a very simple calculation or a calculator sort of a problem to solve. It might require some sort of a reasoning behind the scene. So in an agent loop, the number of reasoning step is not fixed in advance. It emerges dynamically from the interaction in between. Like when if I'm asking like what exactly is a 17 into 24, something like that. Okay, so in that case probably it will be able to give the answer in a single go. But when we are asking any complicated questions like that, so now you might be thinking, in this agent loop, the agent doesn't magically know the number of steps upfront, right? So how does the number of steps emerges? Here, the idea is the LLM or the executor proposes the next action or the next instructions, and the orchestrator, the controller, decide whether to accept, retry, or do a tool calling, or do a termination. So, uh, like to answer the question, who determines that whether the LLM is going to get the next step or not, that the answer is orchestrator. And LLM, what it will do is it will keep on proposing the next action, and the orchestrator, it decides whether to actually execute, or tool call, or terminate. And as per the termination budget or the termination call, so generally there is a certain schema that is being prepared upfront. Whether it matches those schema or not, or some kind of a verification is passed or not, or whether any further action is needed or not, like any signal generally we create in our JSON, that now I am done. We will go a little bit more into these details in our future videos, but this is the very basics of the AI agent looping. If I have to summarize what we learned about agent loop, through prompt engineering and through the structured output, like with a system prompt, like break down the problem into steps. After each step, ask, do I have the final answer? If yes, then output as done equal to true. So in that case, that done signal will go. Okay. Otherwise, the done will be false, and the next step will be keep on elongated. Okay. And over the time, when we get this done equal to true or some kind of a fail-safe limit we reach, that um, that is the explicit call of the termination. So this is the explicit part of the model's output, and there is no other external hook or anything that we have which would tell that this whole LLM plus this orchestration process that you stop now. It is a intrinsic part within where the executor, the orchestrator, the LLM, everything comes together and they execute it. So now let's take a actual real life scenario example and try to understand how exactly the memory is being optimized in the real time in the real life AI systems. So suppose we are creating a code review agent, and the memory management is going to be a very important part of it. Let's see why. In code review agent like CodeRabbit, you are building an AI agent which is going to read each file in your pull request, right? It is going to analyze the code quality, it is going to check for the bugs, and it is going to verify whether your tests are there or not, and then at the end of the day, it will generate some review comments. So the challenge over there is, like if you have a large or gigantic peer, the pull request, when I say peer, it is the pull request, you have like around 50 files into it, and if the agent processes each file sequentially, so by the file X or by the file number of Y, for example here I have written file number 30, the context window is full. So suppose 128k or 250k, this sort of tokens are being consumed by the previous 29 files. How are we going to architect that agent's memory system with that? So the uh, the technique that is being used over there is it has a quite funky name. We call it like hierarchical memory of semantic compression. Okay, so I'm not going to go into that technology jargon details, but like I will just still write it so that later you can actually refer to it. So what happens over there is like it does the full file analysis, and then against each file it like after sending it to LLM, against each file it will create a summary and some sort of a severity. Okay, so suppose we see a issue which is a very high impact one, so with line by line comments, we come into a one line summary or a two line summary or the severity. So suppose the severity can be high and the summary probably will be somewhere around a two line summary. Okay. Now from the file, suppose that file had like 300 line of code, we are down to the two line. So this is how the semantic compression keep on happening. So from full file text with the and the line by line comments, we are coming on to one sentence and one severity. We are not going into the details of a big picture, and then we keep on assigning this severity key code as well. And during the final review, like it will we are going to do all the collection of it, and during the final review what we will do is we are going to discard the low severity one, and the top suppose k number of high severity or medium severity we are going to put to the user, and the LLM attention will be completely onto this particular high severity files, and again a analysis loop will run that what are the changes it can suggest by taking all the files together. So here is the thing that we discussed the other time. So here the around the file analysis loop around the files with um, high severity issues. Okay, so with the analysis loop around the file, we will keep on generating the final review comments with the analysis loop, and in the end we are going to output it to the LLM. Output it to the LLM, and LLM then will do the final processing and send it back to the user that it is your it is your final review comments. So if I see this whole thing, that semantic compression that we talked about, the nature of it is kind of a lossy compression, right? Like we are doing some sort of a compression, and here we are completely fine with this lossy compression because the fine details, like sometimes whether a comment is missing or not, those sort of things we do not really want, right? So here we are putting the decision critical signals, and based on it the final output is generated. Now, what exactly is the advantage of this approach, like where we are doing this summary of two line and only taking the high severity one? So there is no context window overflow because we are keep on getting the first top k numbers. If you see here, what we wrote was the top k numbers. So even if like there are probably 200 severity, among the severity also we are going to do some kind of a segregation, and we will take probably only the top 20, top 30, something like that, based on the configuration and probably the token window the user has subscribed to. And with this there will be no context window overflow, and it scales up to like multiple files, even the whole application it can take, and the cost is also optimized here. And through this smart prioritization we are doing this we are doing this sort of mechanism or the AI systems optimization behind the scene. So how would the code look like if I have to take it on a very high level, like if you have to create your own code review agent, the code would look like something like this. Let's take this Python example. So all the files we are going to analyze independently, and if you can see, like when we are reviewing each files, what we are going to do is like we are going to get the single line summary of it, right? Then we compress all of them. The context never grows because we are compressing them. And how exactly we are compressing them is we are compressing only the first k number of necessary or the high severity ones, and then so these are separate functions, okay, like where we are compressing them, and then after that also we are taking the high severity one, and probably like the first k1 it will get feed into the top summary. So in my memory I will have this as well, so I can probably show this to the user in a different way, and this top summary will be my analysis for my further analysis. And the final context that we create with the file name, the summary and the severity, and then we further feed it onto the LLM, like this step that we talked about. Then the final context we are going to create with a final prompt, and these are the top issues, and now write a pull request review, and then whatever the output the LLM gives, that we are going to put it into our this holistic review variable, and this holistic review variable we are going to output it to the user. Now again, the advantage of this thing is, if we are just having three issues suppose, then under the top summaries all the three issues will come. So this is the way any kind of code review agents, like within Cursor, if you see, there is a certain code review agent. By the time the video is getting recorded, it is Cursor is marketing it heavily. There are things like Code Rabbit. So this is the exact mechanism that they do behind the scene. Now, what if I do not want to miss any record? Uh, till now we have seen that we have missed some record in our last example of this code review agent, and we were taking here the first five, right, out of all the top summaries. But what if I do not want to lose any record? So in that case, let's take a real world example and understand. Suppose you are creating a email extraction pipeline, and out of that you want to get some summary of all the issues that the user have faced into the production, and you can't really lose those emails because they represent the real customer issues. So what we can do in this sort of cases, so this kind of cases are definitely going to overflow our context window. So generally we try to do some kind of a validation or some sort of a compression, and we send all the messages to a queuing mechanism. So in this case, all the customer support systems, it will be in some sort of a queue, like maybe the in Kafka or in SQS. Then in a behind the scene, we are going to perform the summaries. So the advantage of this system is, like, this is not a complete real-time system like code review. In the code review, the user want the immediate response, right? But suppose when we are writing a email extraction pipeline, it can it can be delayed, like it can even run for 6 long hours. And if we have enough LLM tokens to consume, then what we will be doing is we will be sending it to some kind of a queue, and our consumer will keep on processing. So it is going to be completely event driven sort of a thing. And in the end, getting all the details, we are going to create the summaries around complete issue, and there will be a certain level of prompt engineering we have to do to make sure that we are not losing any data. So till now we have been talking about the token economics again and again, that the token is the real currency of the AI system. Now, one of the problem, if you see, that system prompts are repeated again and again. So system prompt, in every request we are sending it. Now uh, I'm going to copy paste a single calculation for you and explain it to you further, what it would amount to. So if we do not really cache the system prompt, so suppose the system prompt is generally quite big one, and with each system prompt it is taking around 500 to 1000 tokens. And for this case, like for a single query with the user query plus the system prompt, the cost would come to us as a 0.16. And remember, this is only for a single query. This is not even like a complete chat. This is just for a single query. This is the amount of cost that we are going to incur. Okay, so in the second request also, you see the same 500 token is being there. And if it is like 50 or 60 token, based on that, like the cost will completely get repeated. So the total cost here, it becomes around like 1650 that you see if only 100,000 requests are there. So OpenAI or Anthropic, they have a default feature to that. This is very important to understand. We do not have to do anything per se. So they have this ability to do the prompt caching. And for that, you do not really have to do anything. You just have to while sending the while sending the message to your Anthropic or OpenAI client, you just have to mention the cache control as the ephemeral type. Okay, and this is going to enable your caching. And in OpenAI, it is automatic for the repeated prefixes. So this thing is, though right now is already being taken care by the LLMs behind the scene, but we also have to like in case we are using any kind of client which doesn't take care of it by default, so we also have to be very careful here, otherwise we are going to incur a lot of cost. So other than this, there are few popular techniques that we already talked about a little bit during our classification related discussion, like during our prompt classification. So one is the model routing. So if these are the simple queries like which can be coming under the FAQ, so then we can use the fast models which are going to be like quite cost negligible affairs, whereas like for GPT 4.5 or GPT 5.2, the thinking or the reasoning models, we are going to have the high valued query, which might be like, suppose there is a very angry customer who is trying to reach out to us, and we kind of get the sentiment analysis that we might lose this customer if we are not answering with the detailed approach. So then we can get our best models to get fired up for those queries. So this is kind of a smart routing that we use. The third optimization that is again very popular is like we can do output token limiting. So LLM can keep on giving you output of a long length, and you are going to just exhaust yourself with the tokens. So if a response is around like 2000 tokens, or like maybe more than that, for example, Google Gemini Pro, I was seeing it is like allowing 65k tokens at times in the response. So what we can do is we can set an explicit limit of a max token into this. So this is also a very important optimization into the systems while we are building our front end or the back end, that this is the highest number of tokens that we are going to reply. So we know that in a single chat, we will not go beyond a certain expense. So other than that, like we also discussed, but I will just put it for the revision purpose. So suppose there is a very verbose prompt that the user has given, or over the time our context is growing, so we are going to compress it to a key point. And if you see, like if you are using any kind of real world coding agent these days, for example, you take it like Cursor or GitHub Copilot, here you will see that after a certain time, what GitHub Copilot will start doing is like it will show you it is summarizing your conversation. So not only at the like a system prompt or the user prompt level, so this summarization happens during the whole conversation only. So it gives a great user experience, like you do not really exhaust your cost runway by any means, or your token limit, the 200k, 272k, whatever the token limit the models have given you. So uh, this is this is going to give us another cost saving model for our token economics optimization. Now, after all of this, there can be multiple loops and the agent loops and the chain of thought mechanism, everything that we talked. We could, as a backend developer and as a SRE, system reliability engineering, and the platform engineering initiatives within our organization, we always should do a cost runway protection. So suppose this is a completely real life scenario. In AI chatbot has a bug in an agent loop, and so you go there and you fix something into the agent loop, and due to that fix, or due to that whatever the a small correction that you uh, did in your code, a bug got introduced and that bug got deployed. So once that bug got introduced, there will be like the agent loop will run in an infinite manner, and you found that $2,700 is burned in 35 minutes. But this sort of thing shouldn't happen into the production systems at all, because if this agent is running across region, across the globe, then this $2,700 can be $200,000. And this sort of things, any AI startup might run into a problem. So, what kind of architecture can prevent this? Let's talk about it. So, suppose we are having this chat API, and alongside that, we are going to introduce this cost guard. In cost guard is nothing but application layer logic. So, every message that we are going to post, so it has to go through the cost guard or this token optimization layer. What generally we do is we will see that whether it is an emergency mode or not. Like emergency mode might be like a single request, whether it is going beyond $5 or a $10, then we will try to mark that emergency mode on, and we are going to give the user a service blocked, or try it with a new chat. Your context window is overflowing some sort of a like a user friendly message. And also with the emergency mode, like generally we have a hourly budget sort of a thing set. If we have a AI chatbot for every region, or for every for every region, or for every servers that we have, and if the budget is exceeded, we are going to block it. And in case it is within the budget, then we will keep on do the iteration. So this is kind of a the cost guard mechanism that generally we put in place. And this layer can be implemented in multiple ways. So I will just give you some basic code example, so that it is kind of clear to you in case you want to implement into your production system. So you can just go here and see like there are multiple layers we have built, right? Like hourly budget or emergency mode. So similarly, in the code, the first thing we need to do the rate limiting, that is the user rate limit, that if the user ID is making more than 60 requests for a given minute, then like for a given minute, if it is making more than 100 requests, then uh, maybe his account got compromised, or multiple people are using the same account. So rate limit might be exceeded for that user, and we need to return from there. And also, like if we just see that the hourly spend is keep on increasing, like in multiple models, for example in the cloth free also, if your hourly spend is beyond a certain limit, like 5 messages or something, then you are going to say that your hourly budget will again get restored in next 1 hour. So wait till this point. And also there are other things like the daily budget sort of things. Also alongside all this emergency mode, and you can have your own logic, how you want to optimize that particular client or that particular person who is using your API. And this kind of observability that we were talking about are the responsibility of generally the SRE. So this observability are the part of the dashboards. So we generally build dashboards around it to just understand that whether this is really making any sense or not, to to apply all those boundedness to the application, and based on that we do our monitoring stack. So when we are talking about our monitoring stack now, it is not at all different than the actual monitoring stack we have in our other real world applications. So we have like a AI app, um, AI API, suppose, like which is a wrapper around your chat GPT. And generally this AI API that you have like in your server, you are going to have your Prometheus client library on top of it, Prometheus or any kind of scrapers. So if you are not aware of Prometheus, what it does is, it is basically a scraper that would listen to your health matrices, and the matrices that you expose, it will then send to your its own server. So you will have a separate Prometheus server. So this there is going to be a Prometheus client that will be configured at your AI API, and from Prometheus client it will go to your Prometheus server. I'm just writing as prom server, and in this prom server you can then do all kind of like alerting or the fire alert query in case you are going into a emergency mode, your system is going into some kind of a emergency mode. So this sort of things we can design on top of Prometheus. So this is a very basic monitoring stack, like any current application that you are building, how they are being monitored. AI application monitoring is going to be not different, but the economics will be uh, completely around the token as well, alongside other than the latency, the load, plus the token optimization. So when we are building it, so latency plus load plus error. Alongside that, the most important thing is the token economics that we were talking about. Token economics. Okay, so these are the things that we need, um, and on top of it, to visualize these things, you can have your Grafana dashboard as well. So again, just at the cost of repetition, this is completely as per whatever the basic systems that we are building, and alongside that the token economics has to be taken care. So before finishing this video, let's take some real world backend AI system. So as a backend engineer, uh, the moment you are generating a bot sort of a system where you are giving the user a real time response back, so the first thing we have to keep in mind that our streaming token should be reaching to the user in a periodic manner. It shouldn't be like in a single go. We do not want to dump all the response. Like if you just write it to the chat GPT or Gemini, you will see that the tokens are being streamed into that, and in the as a user, you do not really have to wait for given x second, 5 seconds or 10 seconds for the whole response, but you might see that the whole response is coming like probably at a span of 10 seconds or a 15 seconds. So what exactly the protocol we are using? We are using HTTP SE, or the server side events here. So server side events are like pretty easy to implement with the OpenAI or the Anthropic wrappers. So they have this streaming capability inbuilt in their request parameters which we are sending. So in the messages, suppose we are sending this role and content, alongside that we are also going to send whether to stream or not. And once you are getting the streaming, it is a very simple code. We are going to send the this response back in a or we are going to parse this response back in a streamed manner. As you can see, for each chunk in the stream is keep on coming. We have some sort of a stopping condition, like where there will be done, and we will keep on consuming the stream, and we are going to put it in our the token variable. So once it is being done, we are going to put a additional data called done. So how front end can very easily, like any JavaScript application, can consume that? They will just have a similar kind of a loop in terms of a event listener. So if the event data is done, then they are going to close the event source. So it is a very simple backend and the front end model we can design here. So this is the backend that we were talking about, and this is the front end code that we are talking about. Okay, so now this gives us a great performance across, that the backend will be keep on consuming the stream with with a stopping message of this data done. So if we are getting this done in any way in our messages, that means we are going to we can actually close our event source stream. So This is the exact way how ChatGPT or any chat application like ChatGPT or Gemini or Qwen, they are being architect or in designed in this same way. A simple SSE or the server-side events that are being sent, and at your JS end, it is being consumed as it is. And another important aspect of this backend engineering is like we often have to do uh, parallel task. Like we have to retrieve the documents, we have to do some kind of a reasoning, and also apply some sort of a safety policy, and keep on generating a draft reply whatever the response we are getting. So uh, generally a parallelism is very much important within our chatbot. So let's take this example. So when a user message comes, we have to find all the retrieve relevant documents from our vector db, suppose, okay, and we have to check whether the response that we are getting, there is a certain guardrail it satisfies or not, like it is not containing any kind of not safe for work or any kind of violent material within it. And then based on that we are going to generate incrementally a draft reply. But all of this thing can happen parallelly. The moment we whatever the things that we are getting as a retrieval and a compliance, and we can keep on feeding it to the draft in a parallel manner. So in that case, like we use async io gather. If it is c sharp, it is like a task when all. So this sort of optimization we can further do in our application. So from the DevOps perspective, also let's see what are the basic architectural things we need to understand while building your AI system. So the first thing that we need to understand is the difference between the RAM and the VRAM. So why AI infra cares so much about VRAM? VRAM is basically video RAM, and the RAM is whereas is the system memory, and they are used to store data temporarily, but they are built for completely different workloads. Okay, so this is something we need to understand while understanding the DevOps. From the DevOps or the system infra perspective, they are built for different workloads. Okay, so when we are talking about RAM is basically like it holds the OS files, the application data, the pre-processing tasks, the batching sort of a thing, and even the model weights before they move into the GPU VRAM sort of a thing. It is going to do all sort of things in our AI system. And what does VRAM do? VRAM is basically like is the memory of the GPU. So the first one is associated with the CPU, and this is associated with the GPU. So it is a high bandwidth memory located physically on the GPU. This is important point. Physically in GPU, it is it is physically getting located there, and it feeds thousands of GPU cores in a parallel with a minimum latency. And what it stores like the model weights, the activation, all the model calculation that goes around it. So all the calculations around the LLM, this thing goes in through our VRAM. Okay, so the core operations of deep learning, if tell you, like there are two things basically: the matrix multiplication and the tensor ops. These two are very important things: the matrix multiplication and the tensor ops. So these two things are being controlled and operated within the VRAM. So where does the DevOps, why does DevOps care about it? DevOps care about it because suppose you want a K8 or the Kubernetes as DevOps, you want a K8 cluster to get up and running where your model is going to run. So all these things you need to take care that if you are running a 7 billion model, what exactly is the GPU capacity that you are going to need. So this sort of calculation again, I want to put into your brain, because probably like you might be using within your application complete set of managed platform, like getting the data from somewhere like Bedrock or Azure AI Foundry. However, in case you have this like host versus buy, this sort of debates, you need to start from here to understand the amount of cost your VRAM or the GPUs that is going to take from your organization to host a certain thing locally, a certain model. Take any open source model. Now there are so many models which are open source, like even the Gemini Flash, which are like one of the flagship model of Google, that is being open source and placed in the Hugging Face. So all these things we need to take care during our decision as terms of the money, as terms of the infrastructure or the operational, the OPEX cost, the CAPEX cost, the capital expenditure that we might need to incur from the pocket. So let's take a very big tech example. For example, Cursor or GitHub Copilot. Okay, so these are kind of very much interested for one of the very important part of the developer ecosystem, and this sort of systems are very much interested to understand how much each user is consuming the data. Consuming, and based on that, all the alertings, all the capping, everything is being done, right? So generally, how this is controlled, if you are building a system of this scale, is the AI gateway. So through AI gateway, we are going to route requests to the different models, and the tokenization or the token economics is controlled from a single place. And not only token economics, there can be like the alerting, the incident response, or the capacity planning. So suppose on a certain time, as a as your CTO wants to go for a completely free tier for maybe a 15 days time period during a Christmas. So that time you definitely have to provision more resources. So like the capacity planning or the alerting, everything that we have, it has to be go through a single place, and that is what we call is a AI gateway. So your AI gateway is basically a wrapper on top of OpenAI, Anthropic, Kimi K2, no matter how many models that you are supporting these days, and it gives you a unified place to control the models. If you want to fine tune any kind of model and place it behind your gateway, putting the guardrails and all the other things. So everything that we talked about in a more generic sense, all things are being controlled by this platform engineering architecture. So this is again a very broad topic, and over the next few videos, or in the end where we will be talking about the tracing or the guardrails, there we will go further deep into this. But I hope you got the idea around it, that why architecting like the real world AI systems for the from the backend perspective, or from the DevOps perspective, or from the platform engineering architecture, what are the things you need to take care. And it is not just a simple openai.chat.messages call that we are doing. Rather, it is a full-fledged production system that we need to build as a part of as a part of our whole product. So I hope over this video you got a complete mental model shift, that I use ChatGPT as a wrapper, then from there to I architect AI system, and you probably now understand like how to structure prompts for reliability, how to use like expensive versus cheap models, how to build AI agent loops, and structure your responses for the backend integration, the important things you need for the DevOps or the platform engineering. and the production grade. For any production grade application, these things are of paramount importance. So see you in my next video. Till then, stay awesome. Bye.